When worlds collide, you'll see the most amazing, awe-inspiring scenes ever put on film. The forces of nature unleashed in all their terrifying force. Tremendous tidal waves smashing New York City. The molten fires from the bowels of the earth gushing out to consume our world.
Nearly 60 years ago, audiences thrilled to the destruction of the Earth in George Pal's classic film, When Worlds Collide. Now, the idea of a planetary smash-up is a staple of science fiction, but can it really happen? Astronomers using NASA's Spitzer Space Telescope actually think they've seen the aftermath of such a collision around another star. The story unfolded as Dr. Casey Lisse and his team studied disks around young stars. Once planets have formed, astronomers think there are a lot of leftover asteroids in the system. They occasionally slam together and produce dusty debris. Spitzer's infrared spectrograph was designed to detect the faint glow from this material. By spreading the light out into its component colors, astronomers can look for the spectral fingerprints of different minerals. Our dusty star of interest is a faint speck known as HD 172555. It's about 100 light-years away and 12 million years old, which, compared to our 4.5 billion-year-old sun, is like a baby born a few days ago. Studying its spectrum, Dr. Lisse and his colleagues realized they had found something very peculiar that they had not seen around other stars. Aside from the usual indicators of rocky rubble, they found features corresponding to tektite, obsidian, and silicon monoxide gas. What's strange is that tektite and obsidian are formed from molten materials. Tektites are hardened chunks of lava found around meteor impacts on Earth, and obsidian is volcanic glass. Vaporized rocks can form silicon monoxide gas. You don't get this kind of material by just smashing a couple of asteroids together. The evidence suggests something much more cataclysmic. Imagine what would happen if our moon slammed at high velocity into a Mercury-sized planet. The resulting impact would eject a tremendous amount of molten material into space. As it cooled, it would likely form tektite, obsidian, and silicon monoxide gas, explaining the features seen in the HD 172555 spectrum. It is amazing to think that Spitzer may have caught the aftermath of such an incredible collision. But it's not the first time astronomers have speculated about world-shattering events. In fact, similar things may have happened right here in our own backyard. Mercury is a strangely dense planet compared to the other worlds in the solar system. Now, if it formed from the same stuff as Venus and Earth, why would it be different? A world-shattering impact could be the answer. When planets form, the lighter materials rise, and denser ones sink to the core. Remove the outer, lighter layers, and you're left with a denser planet, once what's left cools off. Looking to our neighbor Mars, we see a massive impact scar in its southern hemisphere. This area, known as the Hellas Basin, must have formed from an asteroid impact long ago. The resulting plume of molten material would have been blasted into space, some of it eventually reaching the ancient Earth. Even closer to home, most astronomers believe our own moon was formed in similar cataclysm. The theory is that a Mars-sized body grazed the still-forming Earth, generating a massive amount of molten debris. The orbiting rubble would eventually clump together, forming the moon. The tektite and obsidian debris from such massive impacts would not last long around our sun or others. Solar winds and gravitational interactions tend to sweep away the dust over time, and in a few tens of thousands of years, the evidence would be erased. In the long history of our solar system, that's hardly a blink of the eye. The evidence may be long gone here, but seeing what may happen when worlds collide around a nearby star shows us it's not just science fiction after all. For the Spitzer Science Center, I'm Dr. Robert Hurt, reminding you there's a hidden universe just waiting to be discovered.